Hi, welcome to you all. We will be seeing some problems on forced vibration. So before starting with the problems, I need to make you understand the different formulas which we'll be taking, which will be used to solve these particular problems. So first and the foremost thing is the magnification factor. In the previous classes, we have done the derivation on magnification factor. This is a magnification factor in the sense of whenever a spring mass system, a spring mass damper system is subjected to an external force, which is a sinusoidal force, then what will be the amplitude of the system? That will be given as A. Okay, and xs is the static deflection, which is taken as F naught by K. So this is the formula which you need to remember here. That is 1 upon square root of 1 minus r square the whole square plus 2 zeta r the whole square, where r is nothing but omega by omega n, which is omega is equal to forcing function, frequency, and omega n is the natural frequency of the system. Okay, so in the next things we'll be studying about the motion transmissibility. So in the motion transmissibility, when you have a suspension system, or when you are driving a vehicle, so the ground will be generating a certain force which will be transferred to the suspension system. What is the amplitude the tire or the axle will be experiencing compared to the driver? That will be given as A by B. Okay, that is the ratio which is being given. So if I take it in absolute motion, okay, with respect to the ground, so this is the formula which we will be getting, that is 1 plus 2 zeta r the whole square upon root, or that is 1 minus r square the whole square plus 2 zeta r the whole square. If I take the relative motion between these two, how much the ground is moving, how much the driver is moving, then it will be r square upon square root of 1 minus r square the whole square plus 2 zeta r the whole square. So next comes the transmissibility ratio. See, the transmissibility ratio of two types, one is motion, one more is the force. So transmissibility ratio is basically given as epsilon, which is force transmitted to the applied force. So that is given as square root of 1 plus 2 zeta r the whole square. So this is the whole square. Okay, uh, divided by 1 minus r square the whole square plus 2 zeta r the whole square. So this is the formula which we will be using. So these are the 3 to 4 formulas which you need to remember. The one thing is the denominator always remains the same, only the numerator part will go on changing depending upon the condition. So we'll be seeing the first problem here. Okay, so this is the first problem which we will be solving here. So in this case, the problem definition says that a machine of total mass 200 kg is supported on a spring of stiffness 16,000 Newton per centimeter, has an unbalanced rotating element which results in a disturbing force of 800 Newton. So at a speed of 3000 rpm, assuming zeta, which is a damping factor, which is equal to 0.2, determine the amplitude of motion due to unbalance. Next, second is transmissibility, and third is transmitted force. Okay, so for this case, if you start with the solution part here, we'll first write the datas which are been given. Here they have given the mass which is of 200 kg, and they have given the stiffness here K, which is 16,000 Newton per centimeter, and then they have given a disturbing force. Disturbing force is nothing but F naught. F naught is given, which is 800 Newton, and they have given the speed here, which is 3000 rpm. Assuming the zeta value, which is given as 0.2, we need to find out the amplitude of motion due to unbalance. Next, we need to determine the transmissibility and the transmitted force. Okay, so if we have a general formula which is A upon xs, which is given as 1 upon square root of, okay, this is because of the forcing function. What is the amplitude we will be getting? So if you consider this will be 1 minus r square the whole square plus 2 zeta r the whole square. So this is the amplitude which we need to find out. Here xs is nothing but static deflection, okay, which is basically given as f naught by k. F naught by k. So in order to do this, here r value is nothing but omega upon omega n. Omega upon omega n. So we need to find out the values of all these and then substitute here to get the value of amplitude. Okay, for this, first what we need is we need to get the value of r here. So in order to get the value of r, we need to have the omega and omega n. Omega is, it can be easily found out, that is 2 pi n by 60. 2 pi n by 60, which is 2 into pi into 3000 divided by 60. So if you do that, you'll be getting, if you do the calculation here, you'll be getting around 314.16 radians per second. We got the omega value. Okay, so you need to find out the value of omega n. Omega n for a spring mass system, which is basically given as k by m. K by m. So we need to convert this centimeter into meter. So what you will be getting here is, this is 16,000. So if you convert it into meter, it becomes 16 into 10 to the power 5 meter divided by mass is how much? It has been 200 kg. So it will be 200. So you will be getting the value as 89.44 radians per second. Okay. So we got the value of omega as well as omega n. Here r is nothing but omega upon omega n, which is 314.16 divided by 89.44. So you'll be ending up it as 3.51. So the ratio is 3.51. So you got the value of r here. We already know the value of zeta. We need to get the value of xs. Xs already we have discussed, that is static deflection, which is given as f naught by k. F naught by k. So f naught by k, if I just substitute here, F naught is the force which is being given as 800 Newton. K is nothing but 16 into 10 to the power 5. 16 into 10 to the power 5. So if you do that, what you will be getting? So we will be getting around, 1 second. Eight hundred divided by 16 into 10 to the power 5. So we'll be getting around 0.00005 meter. So we'll be getting 0.00005 meter. Okay, so we got the values here. So A will be nothing but, that is xs upon square root of 1 minus r square the whole square plus 2 zeta r the whole square. So this is the formula. What is xs here? 0.0005 divided by r we have already found out, that is square root of 1 minus 3.5 1 square the whole square plus 2 zeta r, 2 into 0.2 into 3.51 the whole square. So if you solve this, you'll be getting an answer of 4.378 4.378 into 10 to the power minus 3 meter, sorry, minus 5 meter, minus 5 meter. This is the solution for the first question, that is the amplitude of the system. Okay, so next thing comes transmissibility. So transmissibility is, we need to find out the transmissibility. Just a second. Okay, this is transmissibility. So in this, we have the formula, that is epsilon is equal to, that is ft by f naught, which is given as square root of 1 plus 2 zeta r the whole square. Okay, 1 plus 2 zeta r the whole square divided by 1 minus r square the whole square plus 2 zeta r the whole square. Okay, so here I had just written here, this is a correct proper one, this will not come. Okay, so here when you solve this, the value, everything is being given here, just you have to put the values out of it. So this is a square root here, so this is 1 plus 2 into 0.2 into 3.51 the whole square divided by 1 minus 3.51 square the whole square plus 2 into 0.2 into 3.51 the whole square. Okay, if you solve this, we'll be getting the solution here. So just check the answer. So it will be getting it as 0.151. So we'll be getting it as 0.1.1. 0.151. So next is, they have asked to find out the force transmitted. See, this is force transmitted, this is the applied force, this is the transmitted ratio. So epsilon is nothing but ft by f naught. So if you want to find out ft, which should be equal to epsilon into f naught. Okay, epsilon into f naught. So in this case it is 0.151 into f naught is 800 Newton. So you will be getting around 120.9 Newton. So this will be the value for ft. So what we did is, we found out the value for the amplitude of the system. Next, epsilon we have found out, which is the transmissibility. Okay, the transmissibility ratio. Then we found out the value of ft. Ft is nothing but epsilon into f naught. Okay, so these are the values which we have got. I hope this problem is clear. So we'll move on with the next problem. Solving the second problem here. The second problem, the problem definition is as it is. The support of a spring mass system is vibrating with an amplitude. So remember that the support of a spring mass system is vibrating with an amplitude of 10 meter. Okay, and a frequency of 1000 cycles, 1200 cycles per minute. Okay, if the spring has a stiffness of 2000 Newton per mm and the mass is 1 kg, determine the amplitude of the system. See, this is the problem of support motion or the motion transmissibility. Okay, so motion transmissibility is, this is the problem of the motion transmissibility. In this case, we'll be studying, if you understand this, this is a spring mass system, this is spring, this is damper, and this is a mass here. Okay, m. Okay, so the support is having a motion. If you observe it, the support of a spring mass system is vibrating with an amplitude. So if you see this in the definition we have studied, this is being given as b. Okay, or y is equal to, this is the y motion or this is the x motion. So this y we used to write it as b sine omega t. So this is the amplitude of the vibration of the support, and this is the amplitude we used to write it as a sine omega t. Okay, so in this case we have the formula for that, that is a by b is equal to square root of 1 plus 2 zeta r the whole square divided by 1 minus r square the whole square plus 2 zeta r the whole square. This is the whole square root. Okay, so now what he has asked is, I need to determine the amplitude of the vibrating mass, which means that I need to get the value of A. There are two conditions. In the first case, till here to here, they have not given the value of zeta. Okay, they have not given the value of zeta. If you just observe this figure, so we will be considering the value of zeta to be 0 here. Okay, there is no damping involved. Okay, there is no damping involved because if you see this, this is a spring mass system. So this is a general equation. So if I remove this part, okay, it is just a spring mass system, just a spring mass system. Okay, so where this is the support which is having the motion B, this is the mass which will be having an amplitude A. Because if you understand, this is a spring mass system. So this is a general equation when we write it. Here he has told that it is a spring mass system. If it is a spring mass system, there is no dashpot, means the zeta is equal to 0. So in this case, A by B will be equal to square root of 1. This zeta is 0, it will become 1, and it will be 1 minus r square the whole square, and this part will be 0. So if you can easily remove the square root here, A by B is nothing but 1 upon 1 minus r square. Or if you want the positive values, so I'll be writing it as 1 upon r square minus 1. You'll be getting, otherwise you'll be getting a negative answer. So for modification purpose, we'll be making it as 1 upon r square minus 1. Okay, so this is the formula for zeta is equal to 0, where there is no damping happening. Okay, so what are the datas they have given? They have given the datas as m is equal to 1 kg. Okay, k they have given as 2000 Newton per meter, and they have given the frequency of this base, which is f is equal to 1200 cycles per minute. So but we need to have cycles per second, because the frequency whatever we calculate, we'll be calculating with respect to cycles per second. So for that case, what we'll be doing is f, we will be taking it as 1200 divided by 60 to get it in cycles per second. So it will be how much? 20 cycles per second. So next what we'll do is, we'll be calculating the value of the omega and omega n, because only r square is required. Okay, so if you do that, what is omega n? Omega n is nothing but root k by m, root k by m. So it is root of 2000 divided by 1. Okay, 2000 divided by 1. So you will be getting like 44.72 radians per second. Okay, so this is omega n value. What will be omega here? Because here linear frequency is given, I have to convert this linear frequency into circular frequency. The formula is omega is equal to 2 pi f, 2 pi f. So for that case, what you will be getting? 2 into pi into 20. So you will be getting it as 125.664 radians per second. Okay, radians per second. So I have to just get the value of r here. R is nothing but omega upon omega n. So omega is being given as 125.66. Okay, 664. Omega n is 44.72. So you'll be getting it as 2.81. So what is the value? We have A by B is equal to 1 upon R square minus 1. Okay, so B is being given, we need to get the value of A here. Support motion is being given, that is 10 mm. Okay, that is 10 mm is being given. So if you see this, A upon 10 is equal to 1 upon 2.81 the whole square minus 1. Okay, so if I solve this, I'll be getting the amplitude as 1.45 mm. 1.45 mm. So next comes this value, this thing. If the dashpot with the damping factor, now initially it was like this. Okay, this is a general equation. Initially it was like this. Now they have introduced a dashpot here, which is having a damping factor of 0.1. So what will be the amplitude? The same formula, this is the formula we need to just use it here. So it will be, second case, it will be A by B will be equal to square root of 1 plus 2 zeta r the whole square divided by 1 minus r square the whole square plus 2 zeta r the whole square. This is the formula. So you already know that A is the amplitude we need to find out. 10 mm is being given here. So square root of 1 plus 2 into 0.1 into 2.81 the whole square divided by 1 minus 2.81 square the whole square plus 2 into 0.1 into 2.81 the whole square. So if you solve this, you will be getting the amplitude as 1.658 mm. So this is how we'll be finding out the solutions for the support motion. Okay, so that is motion transmissibility. The base is exciting, how much is the mass will excite. Okay, for that case, this is the typical problems where we'll be using this formula. Okay, the support motion or the motion transmissibility formula. Okay, here only case is there was no damping initially, and the later case there is a damping of 0.1. So you will be getting this particular solution. So this will be the second problem. Next we'll be going with the third problem. We'll be solving the third problem. In the third problem, it has been shown that the mass of 100 kg being mounted on a spring mass dashboard system having a stiffness 19,600 Newton per meter and a damping coefficient of 100 Newton second per meter. The mass is acted upon by a harmonic force of 39 Newton at the undamped natural frequency of the system. Determine, first one is the amplitude of vibration of the mass, then there is a phase difference between the force and the displacement, and third case is the force transmissibility ratio. Okay, so the data which has been given here is, so if we start solving this, so the data which is being given is mass is being given of 100 kg. Okay, stiffness is being given of 19,600 Newton per meter. Damping coefficient is being given, that is C is equal to 100 Newton second per meter. The harmonic force is given, which is F naught is equal to 39 Newton. And the condition they have told here is, that is F naught 39, that is 39 Newton force is being applied at the undamped natural frequency. Undamped natural frequency is a condition here, you need to remember. So that is undamped natural frequency when it comes. It says, which means that it is at the resonance state. Okay, which is omega is equal to omega n state. So first is the amplitude we need to find out. Okay, so the amplitude formula which we have already derived in, we have already solved in the previous classes, that is A upon xs is equal to 1 upon square root of 1 minus r square the whole square plus 2 zeta r the whole square. Okay, so in order to solve this particular problem, they have given two conditions where omega is equal to omega n, and they have given the value of c here. Okay, in that case, so omega is equal to omega n means, so r will be equal to 1. So this will be the first case. Okay, that will be r is equal to 1. So one more thing is, here the zeta value has to be determined. For that, what they have given is, they have given c value. Okay, so we know that zeta is equal to c by cc. Zeta is equal to c by cc. So we got the value of c here. We need to get the value of cc here. Okay, so cc is nothing but, cc has a formula 2m omega n. 2m omega n. So for that case, if you just observe here, we need to find out the value of omega n here. So omega n will be equal to root k by m. Root k by m. So square root of, so 19,600 Newton per meter is being given, divided by 100 kg. So if you do the square root of this, so you will be getting 14 radians per second. 14 radians per second. So now you got the value omega n. So directly what I'll do is, I'll be putting this value here. Zeta is equal to c is 100 Newton second per meter, and cc is 2m omega n. So 2 into mass is 100 kg into 100 into omega n is 14. Omega n is 14. So you will be getting the zeta value as 0.0357. 0.0357. So if r is equal to 1 and zeta is equal to the value here given, so we'll be solving this particular problem here. So a by xs, if you just take the consideration of r is equal to 1, okay, so what you will be getting, this equation will be getting modified here. So here if I put 1, this becomes 0 here. Okay, so what you will be getting here is 1 upon root, if I remove it, it will be divided by 2 zeta. Okay, 1 upon 2 zeta, because r is 1 here. Okay, so if I substitute that, so here if you take this consideration, a is equal to, okay, a is equal to xs upon 2 zeta, where xs is f naught by k. So f naught is given, which is 39 Newton. Okay, and stiffness is given, which is 19,600. So if you take this value, so you'll be getting static deflection as 1.9898 into 10 to the power minus 3 meter. 10 to the power minus 3 meter. So if you solve this, you are substituting here 1.9898 into 10 to the power minus 3 divided by 2 into 0.0357. So if you do this, so you'll be getting an amplitude of 0.028 meter. 0.028 meter. So this will be the solution for the first case, that is amplitude of the vibrating system. So this is being given, or amplitude of vibration of the mass. Second is, if you just observe, what they have asked is, in the second case they have asked the phase difference between force and displacement. So for this, to get the equation of this, so we need to go for the first derivation, that is magnification factor derivation. So in that we had plotted a vector here, so which was like, there was a k vector, that is ka. We had plotted the velocity vector, that is ca omega. We had plotted the acceleration vector, that is m a ma omega, okay, so ma omega square. Okay, this was the equation which we had plotted. Okay, so here this was the forcing function. This was the forcing function. So if I draw the coordinate axis here, so we'll be getting here as the whole thing here as omega t, and this was phi. Okay, so if I plot a graph or plot the parallel line here, this becomes ca omega. Okay, ca omega. So I want to find out this is f naught here, this is f naught, and this is the vector. So what is the phase difference between the forcing function and the displacement? Displacement equation will be this. Okay, displacement will be this part, forcing function will be this part. So if I draw this perpendicular line or parallel line with respect to this CAW, so I'll be getting this triangle. Okay, so this triangle, if I take this triangle and solve it, the phase difference will be between this line, this force and this. So what will be this distance? So it will be Ka minus Ma omega square. Ma omega square. So if I take the angle, so I'll be taking an angle tan phi here. So tan phi will be Ca omega divided by Ka minus Ma omega square. Okay, Ka minus Ma omega square. So if I take A as a common term here, this gets cancelled. So what you will get here is C omega into K minus M omega square. So in this case, what happens if I take K common on both the sides, numerator and denominator? So what you will be getting, C omega by K divided by 1 minus omega square upon omega n square. Omega square upon omega n square. So your final equation, this we have solved it. How, what will be the value you will be getting here is, so this is tan phi. So what you will be getting here is tan phi will be equal to, this C omega by K can be written as 2 zeta omega by omega n. So divided by 1 minus omega square upon omega n square, or in the short way we can write it as 2 zeta r upon 1 minus r square. So this is tan phi. Okay, if I want phi here, phi will be equal to tan inverse of 2 zeta r divided by 1 minus r square. So this would be the formula. So if I solve this with for the value of omega is equal to undamped condition, where omega is equal to omega n. Okay, so what happens? This becomes 0 here, that is r is equal to 1. This becomes 0. So 0 tan inverse infinity. So tan inverse infinity will be giving you as sine 45. Sorry, angle will be 40. Angle will be 90 degree. 90 degree, not 45 degree. Angle will be 90 degree. So this is how we'll be solving the phase difference. This is the formula between the forcing function and the displacement. Okay, so if some random value of r is given, you can just substitute and get the value of r, as we are taking it for undamped condition. Okay, undamped forcing function where omega is equal to omega n. Okay, so it is a resonance state. So next will be the third case. In the third case, what we are doing is we are finding out the transmissibility ratio, that is force transferred to the applied force. So your formula, already we have know the formula here. So it will be 1 plus 2 zeta r the whole square, okay, upon 1 minus r square the whole square plus 2 zeta r the whole square. This is the formula. So if you say once again the same case where it is omega is equal to omega n condition, okay, in that case r is equal to 1, because already they have told the case here. Okay, the case is undamped forcing function is being given. In that case, so what happens here is, so we'll be getting the equation, if I put substitute r is equal to 1 here, So we will be getting it as square root of, okay, 1 plus 2 zeta square, because r is equal to 1, divided by 2 zeta. Okay, so if I substitute the value of zeta here, so square root of 1 plus 2 into 0.0357 the whole square divided by 2 into 0.0357. So if I solve this value, I'll be getting it as 14.04, that is transmissibility. Okay, this is the transmissibility ratio we'll be getting. So this is how we'll be solving the problem. So you need to understand the question here. So whatever the question we have solved here, so he has already mentioned, this is the main important thing here. He has told that it, the mass is acted upon a harmonic force of 39 Newton at the undamped natural frequency, which means that at the forcing function, which is frequency omega, is acting at the undamped natural frequency, which is the condition as omega is equal to omega n. So with respect to this, I'm just substituting the values and getting the values for amplitude of vibration of the mass, phase difference, and force transmissibility. So like this, we will be solving the problems. Okay, we'll be solving this problem here. In this particular problem, the problem definition is a spring of an automobile trailer are compressed to 0.1 meter under its own weight. Find the critical speed when the trailer is traveling over a road with a profile approximated by a sine wave of amplitude 0.08 meter and wavelength 14 meter. What will be the amplitude of vibration at 60 km per hour? So what they have asked is, there is an automobile trailer. Because of its own weight, the spring gets compressed by 0.1 meter, okay, under its own weight. Okay, find the critical speed when the trailer is traveling over a road with a profile approximated by a sine wave of amplitude 0.08 meter and wavelength 14 meter. Okay, so the vehicle is traveling over a profile like this. Okay, so the if you take this as a trailer here, so there is a spring and this is a wheel here. So when it goes over this profile width is of 0.08 meter and the wavelength is 14 meter. Okay, so for this case, what they have asked is what will be the critical speed. So critical speed is with what speed the critical, in the sense the resonance might happen there. Okay, for that case, we'll be using the simple formula here. First, we'll be finding out what is the value of omega n. Okay, what is the value of omega n and at what speed the critical speed might, and that is the speed at which the critical the resonance will happen, we need to find out. For that case, whenever we need to find out, omega will be equal to omega n. So we need to find out first omega n value. So the spring is getting compressed under the own weight, that is the trailer's own weight. For that case, the omega n formula will be equal to square root of g by delta. This is the formula you need to remember. Okay, when there is no mass given and the body is being compressed some distance by its own weight, then we'll be using g by delta as the formula, as we have discussed in the earlier cases. So if I see this is g will be 9.81 divided by delta is 0.1, that is the deflection. So if you see, omega n will be equal to 9.9 radians per second. 9.9 radians per second. So as the lambda is given, and that is the wavelength is being given, and we need to find out the speed here. So I'll be using the simple formula: speed upon, that is frequency, is equal to speed upon wavelength. Speed upon wavelength, this formula I'll be using. Through this I'll be finding out the speed. Okay, so in order to get that, here this is a circular frequency. For that I have to convert it into a linear frequency. We know that omega n is equal to 2 pi Fn conversion. So what will be Fn? Fn will be omega n upon 2 pi. So this will be the formula. Okay, so what I'll do is, so we have Fn is equal to 9.9 divided by 2 pi. 9.9 divided by 2 pi. So you'll be getting 1.576 cycle per second. Okay, so now you got Fn value, you know the wavelength, you'll be directly getting the speed of that. So speed will be in the form of meters per second. So frequency speed will be equal to frequency into wavelength. Okay, so if you just check this, frequency is how much? 1.576 into lambda is how much? 14 meter. TB 14 meter. So your value will be, it is 22 meter per second. 22 meter per second. So if you convert this into kilometer per hour, so you will be getting 79.2 kilometer per hour. Okay, 79.2 kilometer per hour. So this is the speed where the resonance will happen. If I maintain the vehicle at this particular speed, there will be lot of vibration. Okay, so find the, what they have asked is, now find the amplitude of a speed at 60 kilometer per hour now. So what they have asked was, what will happen at the resonance, what speed the resonance will happen. In the next case, what they have asked, what will be the amplitude of vibration at 60 kilometer per hour. So what they have told is, they have given the sine wave amplitude, so which means that the base will be exciting, or the base will be exciting by a 0.08 meter. So we have this formula, basic formula we have, that is A by B. A by B, this is the formula we have. Okay, one second. Okay, A by B will be the formula which we'll be having, which is equal to square root of 1 plus 2 zeta r the whole square divided by this is a whole square root divided by 1 minus r square the whole square plus 2 zeta r the whole square. He is asking what will be the speed now, what will be the amplitude of the trailer when it reaches 80 kilometers per hour. Okay, when it reaches 80 kilometers per hour. So for that case, we'll be finding out the speed here. Okay, so the velocity is being given here. So one second. Okay, so omega is nothing but 2 pi fn. Omega is nothing but 2 pi fn. So fn we have already seen here. Fn is nothing but speed upon wavelength. Speed upon wavelength. So the speed is being given here as 80 kilometer per hour. Wavelength is how much? Wavelength is given as 14 meter. So we need to convert this into meters per second. Okay, for that 80 or 60 is being given. 60. Okay, so this is 60 here. So we'll be converting this into that. So 60 into 1000 divided by 3600 into 14. So this will be the frequency. If I substitute that in the main equation, so omega will be equal to 2 into pi into 60 into 1000 divided by 3600 into 14. So omega will be equal to 7.47 radians per second. So this will be the omega value. So through this I can find out the value of r here. R is nothing but omega upon omega n. Omega is given as 7.47. Omega n is 9.9. 9.9. So this is 9.9. So your R value will be 0.755. Okay, so here in this particular case, they have not mentioned any value of C here. Okay, they have not mentioned any value of C. So what we'll do is we'll assume a zeta will be equal to 0. So there is no damping. We are assuming there is no damping because they have only given the spring value. Okay, there is no damping value. So what will be your equation? A by B will be equal to square root of, okay, we'll just check out, this will be 0, this 1 second, so this is 0, zeta is 0 here, this goes off and only you will end up here with 1. Okay, here it will be square root of 1 minus r square the whole square. Here zeta is 0, so what you will end up here is this gets, once again I'll write it, so you will be end up with 1 upon 1 minus r square, 1 upon 1 minus r square. So here the trailer value is being mentioned, that is the base excitation is mentioned as 0.08 meter, so which will be equal to 1 upon 1 minus 0.755 square. So your amplitude will be, just check it out, your amplitude will be 0.186 meter. 0.186 meter. So you need to remember this formula, how to solve, get the value of, how to get the value of V here. Simple it is. This is the omega n formula when there is no mass applied, that is G by delta, if static deflection is given. So 9.81, if I do it, I'll get omega n. This formula you need to remember, frequency is equal to speed upon wavelength. So here they have asked to find out the critical speed, that is a resonant speed. So resonant speed will happen when external frequency matches with the frequency of the natural frequency of the system. So for that case I'll be finding out the speed with at what speed that resonance will happen. So we have done the calculation. In the second case they have given the speed and they have asked to find out the amplitude. So in that case, as there is no C value and there is no dashpot value, dashpot is being present there, only spring is present, zeta is assumed to be 0, and with that case we'll be finding out the value of R through this formula only. We'll be finding out the value of R, and then we got the value of R as 0.755 and zeta is equal to 0. In that case A by B will be finding out, the value will be A is equal to 0.186 meter. I hope the things are clear now. Okay, we'll be solving one more problem on this. Okay, so here the problem definition is as it is. A reciprocating pump of 200 kg is driven through a belt by a electric motor at 3000 rpm. The pump is mounted on an isolator with total stiffness of 5 meganewton per meter and damping of 3.15 kilonewton seconds per meter. So determine the vibrating amplitude of the pump at the running speed due to the fundamental harmonic force of excitation 1 kilonewton. Also determine the maximum vibrating amplitude when the pump is switched on and the motor speed passes through the resonant condition. So if you understand this, what are the data being given? They have given the mass of the pump, which is 200 kg, okay, and the speed is being given. So how the thing is, there is an electric motor which is connected to a pump here. This is pump and this is motor, okay. So and the pump is being it's been kept on the isolator, which is a combination of a spring and a damper system. Okay, so what they have given is the pump is being attached or it is connected to a motor. Okay, and the mass of the pump is 200 kg and the motor rotates at 3000 rpm. So the pump is mounted on the isolator with the total stiffness. K is nothing but 5 meganewton per meter, or you can write it as 5 into 10 to the power 6 Newton per meter. Newton per meter. And what they have given is damping. They have given C is equal to 3.125 kilonewton second per meter. Okay, that is 3125 Newton second per meter, just a conversion. So what they have asked is determine the vibrating amplitude of the pump at the running speed due to a fundamental harmonic frequency of 1 kilonewton. So they have given F naught, which is 1 kilonewton, or you can write it as 1000 Newton. Okay, 1000 Newton. So also they have asked to find out that determine the maximum amplitude of the vibrating amplitude when the pump is switched on and the motor speed passes through the resonant condition. So when the resonance happens, what will be the amplitude, and without resonance, what will be the amplitude? So basically we know the formula, that is A upon XS is equal to 1 upon square root of 1 minus r square the whole square plus 2 zeta r the whole square. This is the standard formula we have. Okay, so first and the foremost thing is, first we need to care for a normal condition. Okay, what will be the amplitude, then we need to go for a resonant condition. So for finding out these values, we need the values of xs, r and zeta. So for finding out, first we'll go with r. R is nothing but omega upon omega n. So omega is calculated as 2 pi n by 60, which is 2 into pi into 3000 divided by 60. So you will be getting around 314.16 radians per second. So this is the value you will be getting. So similarly, if you want to find out omega n is nothing but root k by m. So which is root of 5 into 10 to the power 6 divided by mass is of 200 kg. So you will be getting it as 158.1 radians per second. So here the value of r we need to find out. So r is equal to omega upon omega n. Omega is 314.16 and omega n is 158.1. So if you solve this, you will be getting 1.987 as the r value. Okay, so we got the value of r, we need to get the value of zeta here. So already we know that zeta is equal to c by cc. Okay, is equal to c is being given, cc is nothing but 2m omega n. So c value is given as 3125 divided by 2 into 200 into 158.1 omega n value. So you will be getting here as damping factor as 0.0494. So 0.0494 is the zeta value. So similarly, if you want to find out the xs is f naught by k. So f naught is 1000 Newton, k is 5 into 10 to the power 6. So if you find out the value of f naught, xs, that is 2 into 10 to the power minus 4 meter. 2 into 10 to the power minus 4 meter. So what I'll do is I'll just substitute the values. This is the formula here. A is equal to xs upon square root of 1 minus r square the whole square plus 2 zeta r the whole square. Okay, so now xs we have found out, which is 2 into 10 to the power minus 4 divided by square root of 1 minus r we have found out as 1.987 square plus zeta we have found out 2 into 0494 into 1.987 square. So if we solve this, okay, we'll be getting the value as 6.77 into 10 to the power minus 5 meter. This is the amplitude of the system under normal condition. So next we need to go for the resonant condition. Resonant condition. Resonant condition. Okay. Resonant condition. In this resonant condition, what is the resonant condition? Omega is equal to omega n, which means that R is equal to 1. So we had a formula A is equal to XS upon square root of 1 minus R square the whole square plus 2 zeta R the whole square. So if I substitute R is equal to 1, so what will happen here is A is equal to R, if I put 1 here, it becomes 0. Here 1, if I put it, so it is 2 zeta square. So what will end up here is XS upon 2 zeta. XS upon 2 zeta. So what you will be getting? XS value is 2 into 10 to the power minus 4. 2 into 10 to the power minus 4 divided by 2 into 0.0494. Okay, so what you will be getting here is 2.0243 into 10 to the power minus 3 mm. Minus 3 mm. To check, not mm, it is meter. Okay, it is the meter value. I hope this is clear. Okay, so these are the problems which we'll be solving. So simple condition it is with normal case and without the normal case, that is the resonant condition. Okay. So we'll be solving the next problem. In this particular problem, a 35 kg block is connected to a support through a spring of stiffness 1.5 into 10 to the power 6 Newton per meter in parallel with a dashpot of damping coefficient 2 into 10 to the power 3 Newton second per meter. The support is given a harmonic displacement of amplitude 20 mm at a frequency of 35 Hertz. So remember this, this is once again a problem of the motion transmissibility where the support is being vibrating and how much the vibration or how much the amplitude is being transferred to the mass, okay, or on the vice versa. So the same thing is happening here. The problem they have asked is they have asked with the absolute displacement and they have asked with the relative displacement. So already I have told you the differences here. So the differences were A by B, one condition is there where A by B is given as the same as the force transmissibility equation, that is 1 plus 2 zeta R the whole square divided by 1 minus R square the whole square plus 2 zeta R the whole square. So this is the absolute motion. So the second will be the relative motion, which is given as Z by B, okay, which is nothing but R square divided by square root of 1 minus R square the whole square plus 2 zeta R the whole square. So this will be the relative motion. Okay, this will be the relative motion. So we need to get the value of this amplitude here. Okay, and they have given the support harmonic motion displacement. The support is moving with an amplitude of 20 mm and frequency of 35 hertz, and it has a mass of 35 kg, stiffness of 1.5 into 10 to the power 6, and C value is being given. So for this case, what are the data which is being required here is we need to get the value of R, we need to get the value of zeta here. Already B is being given here. So for that case, what are the data being given here? M is equal to 35 kg. Okay, K is being given 1.5 into 10 to the power 6 Newton per meter. Okay, and C is being given damping coefficient, which is 2 into 10 to the power 3 Newton second per meter. Amplitude of the support is given, that is B, which is 20 mm, and frequency F is being given, which is 35 Hertz. Okay, so first and the foremost thing we'll be finding out the value of R. How to find out? Omega upon omega n. So first, how to find out omega? here linear frequency is given. The formula will be 2 pi f. The formula will be 2 pi f. 2 into pi into the frequency B is given as 35 hertz. So it will be 35. So what you will be getting here is 219.91 radians per second. 219.91 radians per second. So similarly, omega n has to be found out. Omega n is nothing but root k by m. Root k by m, which is square root of 1.5 into 10 to the power 6 Newton per meter, and mass is given as 35 kg. So 35 kg. So you will be getting omega n as 207.02 radians per second. So these are the values of omega and omega n. So R is equal to omega is 219.91 divided by 207.02. So you will be getting R as 1.062. So this is the value of R. So with respect to the problem, we need to get the value of zeta here. So zeta is nothing but C by Cc. C is being given already. Cc is nothing but 2m omega n. Okay. So C value is being given as 2 into 10 to the power 3. Okay. 2 into mass is 35 kg. Omega n is 207.02. So you will be getting the zeta value. Sorry, this is zeta value. So zeta value you will be getting it as 0.138. 0.138. So first we will be finding out the displacement with respect to absolute motion. Okay, absolute motion, which is A by B is equal to square root of 1 plus 2 zeta r the whole square divided by whole square root. This is whole square root. Once again I'll write it. Okay, this is whole square root 1 plus 2 zeta r the whole square divided by 1 minus r square the whole square plus 2 zeta r the whole square. So here we need to find out the value of A. B is given as 20 mm. Okay, into is equal to square root of 1 plus 2 into zeta is being given as 0.138 into R value is 1.062 the whole square divided by 1 minus 1.062 square the whole square plus 2 into 0.138 into 1.062 the whole square. So if you solve this, you will be getting the value of amplitude as 65.17 mm. Amplitude as 65.17 mm. So similarly, if you solve it with the help of second case, that is displacement or amplitude, the displacement or amplitude relative. So if you solve it by relative, that is z by b is given as r square square root of 1 minus r square the whole square plus 2 zeta r the whole square. So in this case, so what you will be getting, z upon 20 mm is equal to, this is 1.062 square divided by square root of 1 minus 1.062 square the whole square plus 2 into 0.138 into 1.062 square the 062 whole square. So you'll be getting the z value as 70.54 mm. So this is how we'll be solving the problem by using absolute motion and relative motion. This is only applicable when the support is having a motion and that motion has to be transferred to the mass. Okay, how much amplitude the mass will be rotating if the support is rotating by certain amplitude with the help of spring and damper system. In the spring and damper system, how much vibration will be absorbed and it will be transferred to the system.